Hello, I'm Seongjun HEO, who studied geometric explanation of class-norm formula. This study includes an elementary proof of the class-norm formula and generalization of ideal. First is motivation. Think of each lattice point as a Gaussian integer as shown in the following figure. Then we can count the number of lattice points on x squared plus y squared is k with unique factorization of Gaussian integer. Let this number be bk. When calculated, bk is expressed as the following expression. As k increases, the number of lattice points inside the circle becomes similar to the area, so the following series can be obtained. I thought this could be extended for all algebraic integer rings. The notations are as follows, and please refer to the previously submitted paper. For n-degree algebraic number field K, let lambda 1 so on lambda n be integral basis of OK. First, we will define the following function to make the correspondence between ideas and lattice points. For integral idea I and its integral basis phi1 so on phi n, f is defined as multivariate polynomial like this. For example, if each variable is an integer, then f is norm of this idea, which is in the idea class that contains I inverse. Let nu be the function from non-origin integer points to the set of integral ideas in I inverse bar, like this. Then, simply, fx is equal to nux. Also, we know that nux is equal to nux prime if and only if there is unit u that sigma phi x is equal to u sigma phi x prime. Let Hn be the set of all f. For f and g in Hn, if there is integer entry matrix A, the absolute value of determinant of A is 1, such that fx is equal to gax, then we say that f and g is equivalent. Then we can prove the following theorem. Fki is equivalent to fk prime I prime if and only if there is isomorphism mu from k onto k prime and mu I and I prime are in same idea class. And please refer to the previously submitted paper for the proof of the theorem. This equivalent relation gives the following good correspondence. First, each equivalent class of set of f is one-to-one corresponded to each corresponding k and idea class. Also, each integral idea in that idea class is corresponded to each lattice points by nu. We can see that the element of this set correspond to the integral idea of OK, and between them, we can define an operation corresponding to the idea multiplication. And we can define an operation that acts as idea multiplication on this set using this method, and please refer to the previously submitted paper. In the example of Gaussian integer, the distance of each point from the origin and the norm of the Gaussian integer corresponding to that point were the same. Also, rotating a certain angle around the origin of each point and multiplying unit corresponding to that angle were the same. To use this tool, we will define and use concept act as length and angle on this set for each algebraic number field K. First, I want to define D. The concept acts as distance from origin like this. The process of defining the concept acts as the angle is a bit long. Therefore, please refer to the previously submitted paper for the method of defining the angle and the theorem used in the process. And this is the concept acts as the angle, and it is defined for 2 points with same idea class, and D is non-zero. There is a number of angle betas. Let C be the number of integral idea whose norm is K in I inverse bar. For positive K, let Tk be the set of points such that fx is K and angle between x0 and x is greater than or equal to 0 and less than 1. If we think about correspondence, there is omega k, c number of lattice points in Tk. In here, omega k is the number of roots of unity. Let S be the set of points that dx is greater than 0 and less than or equal to 1, and angle between x0 and x is greater than or equal to 0 and less than 1. If we enlarge it S, then the number of lattice points inside it becomes similar to the measure of the enlarged area, so we can know that measure of S is equal to this limit. Now let's calculate its measure. We can see immediately from the definition of d and angle that this holds. To eliminate the absolute value, let's introduce a variable n as follows. Intuitively, if angle is a value that corresponds to the fundamental system of unit, n is a value that corresponds to the roots of unity, and plays similar role to angle. Then there is one-to-one correspondence between Rn and this set. Now we can calculate the measure of S by changing variables. If we do the calculation, we will get this. Please refer to the previously submitted paper for the calculation process. Let AK be the number of integral ideal of OK that norm is K. For all ideal classes, adding the formula obtained earlier gives us the following formula. Here, if we know that the residue of the zeta function is 1, we can derive the class norm formula directly from this formula. So we did an elementary proof for the formula that is equivalent to the class norm formula. For quadratic number for q, we can easily calculate AKQ like this, so we can get these series. For more than third order, whether there is a good function such as the Kronecker symbol so that we can obtain such series will be considered as further study. Suppose that the concept corresponding to integer is integral ideal, and the concept corresponding to rational number is fractional ideal. Can we think that the point in this set was actually corresponds to a generalized concept of the ideal that corresponds to real number field? I want to define the generalized concept of ideal that corresponds to B for all integral domain B with characteristic 0. Let B be an integral domain with characteristic 0. Let K be an n-degree algebraic number field, and lambda 1 so on lambda n be integral basis of OK. There are integers pi alpha beta j such that lambda alpha lambda beta is sigma pi alpha beta j lambda j. Let Bk be a B algebra that is equal to direct sum of all lambda b with multiplication like this. Then Bk is commutative ring with unity. Let's define NR for the element of B like this, Bk like this. Let Q be field of quotient of B. Then we can also define Qk. For R in Bk, if there is inverse of R in Qk, let's say that R is invertible. Then we can prove the following theorem, that R is invertible if and only if and R is non-zero if and only if R is not zero divisor. Please refer to the previously submitted paper for the proof of the theorem. Let's say that J is Bk ideal when J is subset of Bk and J is OK module, and there is non-zero A1 so on A and B in Bk that J is direct sum of all AZ, or J has only 0. Let's say that Bk ideal J is invertible Bk ideal when there is AL with non-zero AL. Then we can prove the next theorem. Please refer to previously submitted paper for the statement and proof of the theorem. Define ideal multiplication like this, then we can know that if J1 and J2 are invertible Bk ideal, then J1, J2 is also invertible Bk ideal from this theorem. Then let's let IKB be commutative monoid of all invertible BK ideal about ideal multiplication. Then Fk is IKQ. Let PKB be the set of invertible BK ideal, which is ROK for some invertible R in BK. We can know that IKF per PKF is isomorphic to ideal class group of K for characteristic 0 field F. Then conclusion. By using the correspondence between ideal class and multivariate polynomial and between ideal and lattice points and defining the concept that plays the role of length and angle, the following equation was proved. Also, in the case of quadratic integering, special series can be obtained. And this study deals with the generalized concept of ideal and shows that invertible BK ideal has some good properties. Thank you for listening.
Thank you very much. Thank you very much for this presentation. We have well-known scientist Landau. Maybe you know this physician who used to write, "It's obvious that," and finally he hides a very big calculation out of the book. So your presentation was very fast for this type of content, definitely. And maybe we need this presentation to get deeper in the figures. But I would like to ask a couple of questions by the meaning. What is the new, you know, the in number theory, the class number formula models well known. What is the new method or new idea that you realized?
First new idea was I think this correspondence is first new idea, and second new idea is we can make the similar concept acts as distance or angle for all this set. And third new idea was generalization of ideas, so we can see more than we can see all for integral domain B with characteristic 0.
I mean, how why class number formula requires geometric explanation, not just algebraic? Why we need geometric explanation? What it takes for you?
Pardon me.
You mean you provided the geometric explanation, yes?
Yes.
Of class number formula.
Yes.
So why geometric, not just algebraic?
Because it is.
What you get, what you receive from geometry? Idea on something. Why you need geometry for the number theory?
Intuitive and we can see correspondence very visually.
Okay. So it was a hint, and it's the source of idea.
Yes.
And do you have a did you publish it? Do you have a scientific paper?
No,
with your calculation.
Not yet publicated, but I submitted this paper. I submitted this paper to SITF.
Whose authors of this? What is the article?
This is my article for this research.
It's your article. Okay.
Yes.
So it's on the process of publication. Yes.
Not yet.
It will be, or it's already published.
It's not published.
It's not published, but you intended to publish.
Yes, and I submitted to here.
Okay, so it's kind of discussion. Good.
And what are your plans in this research and further?
In further study, I want to think about in here. I want to think about we can get series only for quadratic integer ring, but I want to find some generalized concept of Kronecker symbol. So I want to get series for all algebraic integer ring. And secondly, I want to get if and only if condition for k when hk is 1. These two problem is currently I'm studying.